तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have spent a couple of lectures on heterojunction bipolar transistor, and this is our third discussion. We would be continuing that. The structure that we just pointed out last time was this, that I had put it on the board, but I thought it is better to put it on a diagram like this. So, this is just to show that you have got the gallium arsenide to make the good doping contact, lower band gap material. Emitter is all gas, base is gallium arsenide, dimensions are all there, 0.2 micron, 0.3 micron, 0.15 micron. This is one of the typical structures that they made. People now talk of even smaller base widths like 0.1 micron to get to frequencies like 100 gigahertz. That is the frequency that people talk of, unloaded of course, just the individual capacity of the device. Collector gallium arsenide. So, you got L gas, gas, gas structure. Now, we just quickly run through what we are discussing to sum up what we have been telling. The beta of the transistor depends upon the ratio of the total integrated doping in the emitter and total integrated doping in the base, and of course, ratio of the intrinsic carrier concentration in the base and the emitter. Now, in the homojunction, this is cancelling each other the same. Now, here you have got this contributing to the beta also. This is a big factor, e to the power of delta Eg by kT. So, I have rewritten the same thing, putting that delta Eg, which is actually positive if the emitter is wider band gap compared to base. In fact, in the bipolar conventional transistor, you have a problem other way. You have a problem where the band gap in the emitter is smaller than the band gap in the base, due to the heavy doping effects. Okay. So, in fact, when you do a device like this, you overcome even that. Just to point out what actually is happening, just one or two sentences I would like to bring out. In a conventional bipolar junction transistor, the band gap in the emitter, even though it is silicon emitter, silicon base, the band gap in the emitter is slightly smaller than that of the base, which actually can lead to the beta which is lower than what you get. You have ND in the emitter and base a big ratio, but this brings that down if delta Eg is negative. The reason, just I want to point out, because we are just in a conventional PJT, silicon, all silicon. Okay. The Eg E is less than the Eg. Okay, due to heavy doping. In the emitter. Just to point out what it is, just draw the energy band diagram. This is not a heterojunction, all silicon, still your band gap in the emitter smaller because of the heavy doping effect. The reason is this: if you have a material which is rather lightly doped, you represent the donor level like this. You represent do not represent it as a continuous level. You represent it by dotted lines like this. Not, it does not imply negative. If you really want to put, you will put plus 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 there to say it is donor. So, you can put it like that, but I am putting just now that dashed lines to tell you that there is sufficient space between the atoms. So, they do not interact with each other. Because they do not interact with each other, the Pauli's exclusion principle holds good still. There are number of states in the same level. Now, if you increase the donor concentration to like 10 to the 19, 10 to the 20 in the emitter or 20 to 21, what happens is each of these levels is interact with each other. So, what is one level split up into a band. So, you get an impurity level like this, band like this, and once the concentration goes something like 10 to the 19 or so, or upper end or 18, this is a donor band. Now, you can see what happens is, if this is a discrete level, that is the conduction band edge. Now, the donor level has split up into a band and merges with the conduction band. There is no distinction between the conduction band edge and this level now. In fact, you do not get any carrier freeze out effect, etc., because all these electrons are in communication with the conduction band. Okay. Now, the Eg, that is supposed to be the Eg. Okay. But the effective band gap is that. Because once the electrons are raised up to this point, there is a continuous distribution of energy levels. It is as if the conduction band edge has come here. So, this is actually delta Eg in the case of silicon homojunction, conventional BJT. Delta Eg is like this, and if you use, in fact, this was one of the topics which was a topic of heavy discussion in the 1980s. Okay. In fact, people used to fight over this issue in the conferences, saying how much is that band gap reduction. Okay. And I think that is all that is ironed out now. So, it depends upon the doping concentration. More the doping concentration, more is the spreading, and larger is this delta Eg. And in this case, the delta Eg is negative, less than the actual band gap. The actual effective band gap is less than actual band gap. This is the heavy doping effect. In fact, if you switch over to a heterojunction, okay, if you switch over to heterojunction, you will have the band gap in the emitter larger, and also you can go down to lower doping concentrations. Okay. So, you do not have that narrowing effect at the emitter. If at all, you may have the narrowing effect in the base, because you may go to higher doping concentration. So, you will have the band gap difference even more augmented. So, in the heterojunction, you have got this thing, this quantity positive, and we just saw. Now, I just brought this in because I just wanted to point out to you the additional benefit that you get from the heterojunction bipolar transistor. You do not have to worry about the band gap narrowing effect in the emitter. Okay. Once you do not have to worry about that, you do not have to be concerned about some of the temperature dependent effects which are coming there, or beta getting lowered because of that. Okay. Now, here these equations we have seen using some values like delta Eg 0.3 and the doping ratio as 1 by 200, you would expect that current gain to be about 2000. That is beta dependent only on the emitter efficiency. Now, we also pointed out last time that the Algas gas HBTs fabricated in Bell Lab, USA, they found that initially the beta was about 30-32 in that range, and also this beta dependent upon the area. Going back further into that, so just wanted to see whether it is the volume recombination that is affecting, because we saw the beta is only due to what we estimated is only due to the emitter efficiency. Now, if you calculate the beta due to the volume recombination, electron current injected to collector divided by recombination current. This is the current injected Qdn dn by d of x. dn by d of x is Np0 by Wb divided by stored charge by lifetime, the recombination current. So, that is that quantity. Now, when you plug in the numbers, reasonable numbers, okay, 2 into dn about 100 centimeter square per second, 10 to the power minus 7 lifetime. We pointed out last time why it is low. It is low because it is a direct band gap material divided by Wb squared. I took 0.1 micron. So, Wb squared is 10 to the power minus 10, that is 2 into 10 to the power 5. So, if you have got 30 beta, you do not have to be thinking about is it this quantity that is affecting the beta. So, what we said further is, okay, then what we have eliminated or what we have not considered is the recombination on the surface. Okay. So, I just draw the diagram instead of going back and forth, just draw the diagram. N plus, N minus or N and then the P base. Okay. But I should not be drawing it too large. The P base, you have it in your diagram, you do not have to draw this and all that, because it is already available there. So, that is the contact, that is a base collector. Dimensions about 0.5 microns, 0.3 microns, etc. Then this is the algas. What we have been considering is only this portion. One dimensional analysis, that current flow is in this direction, there is nothing happening beyond this point. Okay. But what you will see is this particular surface is active, in the sense it is very sensitive, because it is left open like that. There is no oxide. In the case of silicon BJT, you have got oxide on the surface. Okay. So, if just we can come back to that and see one more diagram for silicon BJT. What do you have? You have got a junction like this, N plus, and then you have got the P type base, N minus, then N plus. I am showing the contact at the bottom, it can be on the top also, like in the IC. Here is the contact here, base, then of course you have the emitter. Okay. Here you have got an oxide here, you have got the oxide here. So, this surface here has a protective layer of oxide. Okay. So, that is silicon dioxide, good thermal oxide. So, the recombination velocity, what we talked of last time, in the sense just like in the case of bulk, where stored charge divided by lifetime is the recombination current, okay, you have got recombination current into the surface. The current or the electrons are lost to the surface due to transport of the electrons from here to here. In fact, whatever bulk concentration is here nearby diffuses into surface to recombine there. So, what we said is the surface recombination velocity, surface recombination component is the one that we are talking of. So, just like the bulk recombination is proportional to the carrier concentration, the recombination at the surface also is proportional to the carrier concentration, Np near the surface, just adjacent to surface. So, it is a per centimeter cubed, okay. And S is a proportionality constant, proportional to the carrier concentration multiplied by the area over which the recombination takes place. Okay. If you see here, in this case, that is the area that is recombination taking place, because all the carriers which are injected are flowing like this, okay. but many of them go into that like this. The width up to which it will be reaching will be practically equal to that width. So, I can say that carrier concentrations decays from large number, let us say it is been normalized as 1 here, 1 to 0 here, or NP 0 to 0. Similarly, here it decays from NP 0 to 0. Okay. So, you have to take this area into consideration, and the current going into the reaching into the surface is due to the recombination there, which actually is the recombination current which gives rise to base current. So, that is what we have put here. So, the carrier concentration there on the surface which decays from the emitter edge away to 0, NP 0 to 0 into the area. So, the product of these two gives me actually 1 by centimeter cube into centimeter square. This gives 1 by centimeter. This current is actually charge per second. So, the proportionality constant must have dimensions of centimeter per second. So, if you put it centimeter per second, the whole thing is charge per second. So, this is the current, and this S has dimensions of velocity. So, we call it as recombination velocity. It is not the velocity with which the electrons are moving into the surface. In fact, electrons are moving into surface by diffusion. If you want to solve a 2-dimensional equation, what you will do will be, you will write down the equation del square n minus n by tau equals 0. That is the 3-dimensional equation, and on the surface you will write q n into s is equal to q d n dn by d of x, or in this direction. Okay. So, that is the boundary condition that you put when you solve the 2-dimensional equation. Now, leaving aside that, what we are trying to point out is, in the case of silicon, that recombination velocity is very, very small, because it is passivated with silicon dioxide. So, you do not really have to worry about the recombination on surface, and if you use that 1-dimensional equation, it gives you fairly close results to experimental results, whereas here it is far off. So, let us see what is the magnitude of this. In the case of unpassivated surface, like the one that you have got here, like this one, where you have got the gallium arsenide, a bare surface. In fact, when the Bell Lab people made that device initially, it was a bare surface, and these, there are a large number of density of dangling bonds are present, which give rise to their recombination centers, which give rise to higher recombination velocity of the order of 10 to the power 6, or even higher than that recombination velocity, okay, which would mean that the electron current injected here, quite a bit of that will be reaching here, because the recombination here is not much, but quite a bit of that will be recombining here also on the surface. So, what we have to do is compute that current and see, if you compute the beta by finding out the collector current divided by base current, how much will that be? Collector current will be actually INC, base current will be volume recombination current plus recombination surface, because after all, whatever electrons are lost here by recombination will be replenished from the base, okay, or the electrons when they recombine, they will recombine with the holes, those holes are replenished by the base. Okay. Now, let us see that surface recombination current ISR is actually, this is the same equation that we have written here, except I have put, instead of NPS, I have put it as NP 0 by 2, because if you move from the, in this direction, it is decaying from NP 0 to 0. Similarly, if you take it here, okay, that quantity is NP 0, and up to a width equal to WB, practically it decays from NP 0 to 0. It is a boundary condition here, and if you see the equi-carrier concentrations, if that is 0, that will be 0 there. So, this is WB base width, that width equal to that. So, the area over which the recombination takes place is decided by that width equal to the base width. Okay. Now, the carrier concentration over this area is decided by the average value on this. We can take this area multiplied by the average carrier concentration, and the average carrier concentration is like this. I call this as y. Okay. NP0 at the edge, let us redraw it properly. Y and NP0 at the edge, y equals 0. So, average of that is NP0 by 2. So, what we are telling is the recombination takes place over a width equal to WB from the emitter, and the average value is NP0 by 2. So, that is why you can say the current due to recombination is actually equal to Q into S, that is the recombination velocity, into the average carrier concentration NP0 by 2 into that area. Area is actually corresponding to this width. How you take it will depend upon what is the emitter shape is. Okay. Supposing it is circular emitter of radius RE, your pi r squared is the emitter area, and this area will be pi r plus that width square minus pi r square. Okay. You can see now, if this area becomes larger and larger, this area compared to that will become smaller, because this is fixed by that width. For a given base width, this area is fixed by that. Okay. So, you will see see the equations, you will see it much more clearly. So, what I am trying to point out here is surface recombination velocity is Qs into area, surface area into average carrier concentration, and volume recombination, you know that is proportional to area, and the volume is area, emitter area into base width, and QNP0 by 2 is Q by tau, the whole thing is Q by tau. So, ratio, what we are trying to find out is, should you worry about surface recombination? If ISR equal to volume recombination, you do not have to worry, because we found out that the beta decided by volume recombination is very small, very large. So, the ratio of ISR to IVR is given by these two terms cancel, QNP0 gets cancelled, and S is there, I put it here, AS by A is written here, and the tau n goes in numerator because we are dividing by that, and WB is there in the denominator. So, just cancelling the common term NP0, you get this. So, now you can see how much is surface recombination relative to volume recombination depends upon one, the recombination velocity. If the recombination velocity is very, very small, you do not have to worry about it at all, because that will be negligible. Supposing it is 0, the recombination velocity is 0 or tending to 0, this ISR tends to 0. That is the case of well passivated device like silicon BJT. Now, if it is finite 10 to the power 5, 10 to the power 6, then it will depend upon the ratio of the surface area to the emitter area. Okay. You can see that this actually gives you a clue why the beta of those transistors depended on the area of the emitter. Larger the emitter area, smaller is this ratio. Larger the device area, surface effect is less. So, that is why in literature you will see one should be concerned about surface characteristics in smaller and smaller devices. If you make a smaller area device, particularly in the case of VLSI, you make the device area small, then you have to be concerned about the surface condition. Okay. So, there you are making emitter area small, still you can get negligible surface recombination if S is small. So, AS is the effective area over which surface recombination takes place, A is the emitter area. And to sum up what is said here, the surface recombination effects dominate in small area devices. Area small, that becomes large. Now, let us see the current gain. Let us for the time being pretend that the emitter efficiency is unity. We can do that because it is large, it is very close to 1. If you take that beta, it is about 2000. So, we started looking low, so started taking a look at this because the beta is much smaller than that. So, let us not neglect IVR also, take this into account. The beta is, when the emitter efficiency is unity, the beta is INC, electron current injected to the collector divided by volume recombination plus surface. I can pull this IVR out and then it becomes ISR by IVR. So, what is this quantity INC by IVR? That is the one that we have just now calculated as 10 to the power 5 beta. That is INC by IVR would be the beta if emitter efficiency is unity and surface effects are negligible. That is, this is 0. So, that is beta naught I put. So, beta naught is the beta when surface effects are negligible plus emitter efficiency is unity, and we just calculated that as, if you look back, as 10 to the power, for this example 2 into 10 to the power 5. Okay. So, you get beta is beta naught divided by this quantity. Now, you can see the beta can get affected if the surface recombination current becomes large compared to IVR, and that ratio we have just now estimated as S tau by W into AS by E, just previous slide. ISR by IVR is that quantity by taking these two ratios. I just put that term here, S tau by WB into AS by E. Now, you can see very clearly that ratio of surface current to volume recombination current plays a very major role in deciding the current gain. Let us put some more numbers and see. So, beta naught is the beta when S equal to 0 and emitter efficiency gamma is 1. Let us take circular geometry device. Okay. Surface area pi Re plus Wb whole square minus Re squared, correct, because this is like this now. Looking into the emitter, that is the AE, top view, that is where the recombination takes place, around a ring of width. So, this is Re, okay, and this is equal to, that is equal to base width almost. Okay. So, that is the base width. So, you are trying to find out the surface area over which recombination takes place, that is actually equal to pi Re plus Wb whole squared minus pi Re squared, okay. That is AS, and area of the emitter is pi Re squared. So, the ratio now depends upon Re ultimately, because Wb is fixed. For a given Wb we are calculating. So, you have got pi gets cancelled, Re squared and Re squared get cancelled in numerator, and you have got twice Re into Wb divided by Re squared. I have neglected one term here, which is Wb squared, because Wb is small compared to Re. Okay. Even if the Re is 1 micron, Wb is 0.1 micron, this is 100 times smaller compared to Re squared, or 10 times smaller compared to the Re Wb. Okay. Usually it is much smaller compared to that. So, this is ratio Re gets cancelled. Now, you can see ratio depends upon Wb by Re. So, finally, it boils down how much is the base width decides how much is the ring width, and how much is the area depends upon Re depends upon this ratio. Okay. Now, let us put that number into that. Beta is beta naught, that is substituting in one equation is this, beta naught divided by S tau and W by S In fact, you have just now seen AS by AE is equal to 2W by RE. So, that is why that RE squared gets cancelled because RE in the denominator and W in the denominator gets cancelled. 2W by RE, W gets cancelled, okay, and this has got R the square, RE square, that RE gets cancelled, you get that term. Just plugging in for area ratios, this quantity, you get that. Now, that turns out to be 50. For if I just taken some value which is really small area, where RE is 1 micron, very small emitter, and S is 2 into 10 to the 6. It can be even higher than this, it can be even 10 to the 7 of that order. I just took some numbers to show, magnified the effect and showed that your beta can be 50. In fact, what they have seen in the lab compared to, that is WB is actually slightly different, that is about 0.15 micron, and areas are slightly different. It is not circular, it is square type, square geometry. Emitter. So, top view is like this. I think they have got dimensions which are even as low as 6 microns, 6 microns by 20 microns. Now, here this is the emitter area. Let me not put that down. This is the emitter area, W into length. Okay. If I call this as W, so AE is W into L. Area. How you calculate surface area? Surface area, if you want to calculate, what you need to do is find out a periphery around this of width equal to that, which is equal to that. So, you have that is W, that is L, take this width, that is A of S, this is AE, and this quantity is W plus 2 WB, WB. W is the width of this emitter, WB is the base width. So, this is, so the key thing to note is that find out the recombination current here by finding out the width which is equal to base width and see what the area is, and the carrier concentration is NP0 here, 0 at the other edge corresponding to that. So, this is just as an example. If you have to calculate the beta of the transistor or a square geometry device, all that you have to do is find out that periphery area of width equal to WB. Okay. So, it would matter quite a bit when it becomes smaller and smaller, the length and width, and they have made devices which are large, W quite large and also length large. There the beta approaches closer and closer to the what they have estimated. Okay. So, now you cannot say go ahead make the device area big, so that you can get rid of the surface effect, because if I make RE larger here, that effect goes off. If you take a device which is 1 centimeter area, 1 centimeter square area, perfect, beta is 2000, you will get. But what they did in BL is, once they saw this, they realized that the effect is due to surface, and once they realized that effect is due to surface, because you do not see it in silicon, even in small area devices, they tried to passivate the surface. The surface recombination velocity is large because there are a lot of dangling bonds here. these atoms in the bulk, they are surrounded by 4 neighbors. So, all those bonds are tied to each other, there are no dangling bonds. Whereas, here the atom sitting on the surface has 3 neighbors below, no neighbor here. So, a dangling bond is up there, which is very highly reactive, and that is the one which acts as a recombination center. It is a deviation from the periodicity. So, any deviation from periodicity acts as a deep level, and as I pointed out in the case of Schottky barrier, they are distributed all over the surface, all over the energy band diagram, these recombination centers. So, how do you reduce the recombination velocity? Grow thermal oxide, that is what silicon people did, but you can't grow thermal oxide in gallium arsenide, because when you do that you get gallium trioxide, arsenic trioxide, and the arsenic trioxide reacts with gallium arsenide to convert it to gallium trioxide and release arsenic. So, you will have arsenic on surface. You are not worried about arsenic because it is arsenic. Okay. It is one situation where even it is poisonous to human beings and also bad for the device. It is just putting a metallic layer, similar to putting a layer, an elemental layer on the surface, that actually increases the recombination current drastically. Okay. So, thermal oxide or native oxide of gallium arsenide does not work. So, do not think of putting native oxide on the top of that. If at all you have to get good passivation, you have to remove that oxide completely and deposit some oxide on the top. Now, if you deposit oxide, people try to deposit nitride, oxide, etc. on the surface. No question of putting oxide, because that oxide will react with gallium arsenide to release arsenic. So, there is no chance for you to use silicon dioxide even by deposition for passivation. Okay. See, what I am trying to point out is, over here you must deposit some layer. Okay. Let me remove all that thing now. What you require to do is put a coating on this. If it is here coming, you have to remove it by lithography. So, I am showing it here. This is a passivation layer which protects the junction, which protects the surface. So, you can't put a deposited oxide here. When I say you can't, you can, it is possible for you to deposit, it will not serve the purpose, okay, because that SiO2, any oxygen containing layer, will react with gallium arsenide to release arsenic from the gallium arsenide. Okay. But then you say put nitride, and these are the steps taken by people. Instead of oxide, put nitride. When you put nitride, what happens? You do not get good passivation, because after all, it is, if you have a surface, you should, if you want to satisfy those dangling bonds, the deposited layer must be in intimate contact with the surface. It should interact with the dangling bonds. Okay. Some sort of chemical reaction should take place for the surface to get passivated. When you grow silicon dioxide, it is a native oxide. Silicon is converted into silicon dioxide. So, those dangling bonds are wiped out because of the SiO2. Here, you deposit, it is there lying on the top of that silicon nitride layer, you are happy about a cap and measure the beta, still not good. Even if it is good, it is not so stable, because the dangling bonds are still there. So, here came the Bell Lab people finally realizing that you need to do some chemical treatment. So, they started dipping in all chemicals. For very intelligent way they have been doing. One of the chemical treatment that they were doing was dipping in a chemical called ruthenium. This was happening in 1980-81. Okay. In fact, I used to hear that because I was working on some passivation work at the time. BL, they were dipping in that solution. Some degree of success they got, but the real success came much later, late 1980s. In between, people were trying all the deposited oxides, nitrides, nothing worked. Somewhere in 1987 or 88, they went ahead and did that treatment. Dramatic increase. In fact, a paper was published somewhere around that, saying dramatic increase in the beta from 30 to 1800. If you have gone to 1800, you know what you have done. You have removed that surface recombination velocity or brought it down to 0. That means you have passivated it very well. So, this was actually done, the beta of this. So, those transistors which were very poor improved 1800 when the surface of the base region was passivated by chemical treatment to saturate the tangling bonds with sulfur, gallium sulfide, arsenic sulfide. Okay. So, that is a sort of stable compound. So, what they did was they treated that. I think I will spend little bit of time on this here, because this was one of those problems which was close to the heart in many in our laboratory, okay, including myself. Okay. At least couple of PhDs have come out of this from our laboratory in related to this area, in the passivation and making MIS devices. So, what they did in the lab was they treated with sodium sulfide 9H2O. This is a salt of sodium sulfide. This is a composition. Actually, this is what sodium into the chemical composition of sodium sulfide. So, the sulfur from here, see, when you dip it in the chemical, the solution, you dip it in the chemical, you dissolve this, okay, in water, you get the solution, and then you keep the wafer, the finished wafer, you can keep it in the solution for some time. You can heat it up 50 degrees, 60 degrees centigrade, so that the reaction takes place at the surface. So, sulfur from here passivates the device very well. Okay, the person who did has the name same as mine, Rajaram Bhatt in BL lab. Okay, I know him very well because he worked in RPI with Professor Gandhi. When he went to Bell Lab, he was doing that work. Now, the joy was very short lived. Go up, call the boss. The boss comes and sees the beta is down to hell. Okay. So, in the sense, it is not so stable. One. Number two, the sodium sulfide layer which is on surface gives rise to some leakage current across the junction here. Hey, you do not like any sodium potassium contamination. The sodium sulfide gives rise to leakage there. So, barring that leakage, the beta went up. So, to remove that sodium the leakage, it was dipped in water, the whole thing went off. Okay, though these sort of problems were encountered in that, but ever since then people said, hey, there is something which does the trick and you must work on some other compounds. And then people came up somewhere in 1990s, ammonium sulfide. Ammonium sulfide solution, no sodium. So, when they use ammonium sulfide solution, no leakage current, the layer on the surface could be retained, okay, because the sulfur, and this of course you do at about 70-80 degrees centigrade, and dip it in the solution, keep it say 15 minutes, 20 minutes for at about 80 degrees centigrade, it gives quite a good passivation, no surface leakage, because junction does not have a ohmic layer on the surface, there is no ohmic layer on the surface. So, leakage current is low, people made solar cells, okay. But then somewhere around 1991, I met one of the persons who was working on that, came to India in a conference in IWPST in Delhi. Since I was interested in that, we asked him, how does that ammonium sulfide work out? There was a paper already published in Applied Physics Letters. When he asked how does it work out, he just shrugs the shoulder and says it is almost same as sodium sulfide, but the leakage current is not there. What is the problem? There is some stability problem. The stability problem is because when you put this particular layer, that was found out little later, when you put this particular layer, the surface should be very clean there should not be any oxide layer. Okay. If there is any oxide layer, then that oxide layer will react with gallium arsenide to release arsenic. That is what was happening. The surface recombination velocity was not low enough as you want it to be. There is still a lot of recombination taking place till they observed instabilities. Okay. So, the next following up chemical was a chemical that he put in that, a lot of work went on. People said, okay, I will do all this treatment in high vacuum, take it, prepare it in situ, where you do these depositions, treatments, etc. In MBE system, all sorts of complication things were done, number of papers appeared, but one of the things that succeeded, which was still simple, was stick back to this particular solution, but modify the composition. In fact, you can buy this type of solutions. Ammonium sulphide is available in market. So, next level is ammonium sulphide X, where X is greater than 1. This is called ammonium sulphide solution, which is rich in sulfur, a sulfur rich ammonium sulphide. X is not 1, X is greater than 1. Okay. This solution, there are a lot of reports which have come around that 90s, which said that if you use ammonium sulphide is X greater than 1, 1 to 2 in that range, you can buy the solution. If you use that, two things happen. One, initially that oxide is etched, the thin oxide layer, it is a native oxide which is always present. You take silicon wafer, you keep it open to atmosphere, it reacts with oxygen, you have got SiO2. Similarly, gallium arsenide, you keep it open, it reacts to give you oxide of gallium and arsenic. So, if you just put chemical treatment, you get that oxide thin layer is always present, which will actually react, which will respond when the temperature goes up a bit, release arsenic. With this solution, what happens is, this solution reacts with the oxide layer. It removes the native oxide when it is in the chemical, plus it also removes a thin layer of gallium arsenide. So, you have got, when you do the treatment, you have got the surface cleaned up from the oxide layer and surface also a layer etched out. Any junk that is, to use that language, to any bad layer that is present on surface, that also is removed. You have got a fresh surface exposed, with which ammonium sulphide will react and passivate it nicely. Okay. This was fairly good enough, but even then the stability problems appeared, because this is a thin layer that is put there, covering a layer of covering the gallium arsenide layer. You need to further protection. In fact, this is where we did a lot of work in IIT in the microelectronics laboratory as a part of one PhD program, where ammonium sulphide treatment extensive studies were done with and deposit PECD nitride. So, ammonium sulphide treatment followed by silicon nitride Si3N4 deposition in plasma, by plasma enhanced chemical vapor deposition. You pass silane and ammonia, SiH4 and ammonia gas, they react at low temperature when you provide plasma. Plasma is, you are giving the energy from the electric field, RF. So, you can do this deposition at temperature like 300 degrees centigrade or even 250 degrees centigrade. So, nothing happens to that layer. On the top of that, you deposit this layer. So, now the ammonium sulphide does the job of removing the oxide, exposing fresh surface and passivating the layer. The PECVD nitride put on the top does the job of protecting it from further coming into contact with the outside world. So, when you make devices, in fact, these devices have been made, fabricated using epitaxial layers. When you make devices with this, the field effect on, see actually the way you test it is, use this PECVD nitride as the gate dielectric, take gallium arsenide layer, passivate it with ammonium sulphide, put nitride, put a metal gate, source drain contacts put, you get, instead of MOSFET, you got MESFET, metal insulator field effect transistor. You call it insulator because it is not the oxide. So, it can be anything, nitride. When you put it, you get excellent field effect transistors. In fact, if you like to see an article on this, you can open up the IEEE transactions on electron devices. So, that tells the whole story about passivation. So, just write down that. So, IEEE, a full-fledged paper running to about 14 pages or so, transactions on electron devices, March 2002. That brings you very close to the present day, 2002. I don't remember the page, March is sufficient, March 2002. You see, this is an article written, I think I will put an advertisement for this by Ramashan and yours truly. Okay. So, these are the two authors which wrote this article, which has brought in this stable MIS field effect transistor. Okay. Subsequently, which appeared last year or last March or something, not April or so, 2003, around that time, there was another article which came from the IIT Microelectronics Laboratory on passivation of detector, PIN detector. In fact, if you recall in our initial lectures, we said indium gallium arsenide on indium phosphide can be used as a PIN detector for fiber optic communications. There, same problem. I can have indium phosphide, okay, indium gallium arsenide undoped, and then I can have the indium gallium arsenide p type. Or indium phosphide, does not matter. So, p type, this is intrinsic, this is p type, I am sorry, n plus. These are different layers which are there. So, what I want to try and point out is, this is slightly n minus. So, then you prepare it and etch them down like this. So, you have the junction exposed here. When you have the junction exposed, the whole thing what you have to remember is a PN junction is fabricated using epitaxial layer, you etch it down, so that isolate one device from another one. You are on the wafer, number of devices are there, this surface is exposed. That gives rise to large leakage between the P and N layer. You passivate it, and this passivation is again ammonium sulphide which is being used. So, when you use ammonium sulphide, it is not sufficient if you use ammonium sulphide, you put a coating of another dielectric material. One of the things that is done is PECVD nitride, which worked out very well with annealing etc., because when you deposit PECVD, there are some damages which come up because of the RF. But here, what we have tried out, in fact, as part of some MS degree program, passivate with ammonium sulphide and then deposit polyamide. Here is just spin polyamide. Very easily you can put a coating of that. That gives excellent leakage current. In the sense, when you say excellent leakage, what you mean is very low leakage current. So, you got, it is not excellent means very good leakage current. If somebody comes and says, I got very good leakage current, means very small leakage current. good from the point of device point of view. That polyimide, that is ammonium sulphate passivation followed by polyimide. Okay. Plus polyimide. That gave excellent results. In fact, the authors of that slightly lashed out on the work on this nitride deposition, okay, saying that you see polyimide gives better results because PECD gives some damages. But to be honest, if you PECD when you put the gate, you anneal with the aluminum at 400, it leaves all the damages out. So, these are some of the work which have been done on the passivation, which is important when you make compound semiconductor devices. I will not touch upon other devices. In the next lecture, I will touch upon several other types of heterojunction bipolar transistors, including silicon germanium. Okay, because silicon germanium competes with gallium arsenide. We will see it in the next lecture.